Hi, I'm Benny Cutler. I'm a 10th grade at NSU University School, and I'm here to help you guys study for your AP exams coming up next in a couple weeks. So this is going to be Unit 8 of AP Calculus, Unit 6 and 8 of AP Calculus AB, which is integration and applications of integration. So we'll get started with what an accumulation of change is. So this question's asking, we have this graph and we want to find the area under the curve between 0 and 6. So we'll see why this is important in a second. But first, let's just try to think about how we could approach this. So we have, if we want to just find the area of this space in between the x-axis and this curve. If we look here, we can make this into a square, this into a triangle, and we have some simple geometric shapes that we can work with. So if we look, this is 2, base is 2, height is also 2, this is a square, the area is 4. This one we have 1, 2, 3 times 1, 2, 3 times 2 is 6. So that's the area of that rectangle. For this triangle, we have 1, 2, 3 times 1, 2. And a triangle is 1/2 base times height. So we have 1, 2, 3 over 2 times 2. So the area of this is 3. And we have another little triangle over here with a base of 1 and a height of 2. 2 times 1 divided by 2 is just 1. So we have the area of all of these smaller shapes. And now if we add them together, we get the total area under the curve. So we have 4 plus 6 is 10, plus 3 is 13, plus 1 is 14. So the area under the curve should be 14 units squared. That's units squared just because it's area. Okay, so that's how you find the area under the curve. So what this means is it's an accumulation of change. So we'll get more into this in a little bit, but as we're changing more, so here the rate of change is high, so we're accumulating more change under here, and that can be represented by the area of the curve, under the curve. But again, we'll go into that in more depth in a little bit. So the next thing we want to do is Riemann sums to approximate the area under the curve. Not everything is going to be a simple jagged graph like this where we can separate it into simple geometric shapes. Sometimes we can have a curve. So College Board loves to give you tables to see if you can use those to predict things about a function. So we're asked to calculate the left Riemann sum for the function over the intervals 0 to 8 using the 4 subintervals indicated in the table. So before we start with this problem, let's introduce the idea of Riemann sums and what this means. So we have, imagine we have a graph that looks something like that. Could be any graph, doesn't really matter. Now we cannot split that into geometric shapes to find the area because it's rounded. But what we can do is we can approximate it by making it into geometric shapes. So what a left Riemann sum is you start at the left point, you make a rectangle. So let's say this is 1, this is 2, this is 3, and this is 4. And this should be 3 subintervals or 4 subintervals for doing a Riemann sum approximation. And the question here, this isn't the question, but if we were asked to find a left Riemann sum, we'd start at the left point and draw a rectangle to the next point. So here it's just 0 because the left point is 0. But now here at 1, we use this value at 1. That's roughly the value at 1 for my beautiful graph here. We make a rectangle to 2. And that is one of our rectangles. And if we do another rectangle from 2 to 3, we start at the left point, so here, and we go to 3 and make another rectangle. And we do this for all the subintervals that we're given. And this gives us a general approximation for what our graph, what the area under our graph is going to be. And to find the area of this, we can just find under the curve, we can just find the area of each of these rectangles. So we do 2 minus 1, that length here, which is just 1, times what the height is just the value of the function at this left point because it's a left Riemann sum. So you just plug in that point 1 to the equation or the formula, the function you're given, and then multiply it by 1, and then you add up these rectangles. So that's the idea of a Riemann sum, to approximate the area under the curve using shapes that we can deal with and not curves like this. So now let's go back to the question that we have. Okay, we have this function. This time our subintervals are a little different, but we can still use those. So here we have some function. It starts at x equals 0. The value is 10. So 10. You don't always have to draw this out, but it just helps to visualize. At 2, we'll call this 2. The value is 8. Call that 8. At x equals 5, the value is 2. So 5, that's around 2. 7, it's 4. 7, 4. And then at 8, it's 7. So our graph is going to look something like this, but we don't really know. The point is that we're going to use the left values of this function to make rectangles. So we're going to go here, 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 and oh no, not that last one, because we're only concerned up to this point. Okay, so now what we need to do is find the areas of each of these rectangles. It's a little tedious, but College Board wants to show that you can't just use the shortcuts that are coming up later, that you can actually apply what the ideas mean. So if we find the difference in x from 2 to 0, it's 2. So 2 times the height is 10 plus 5 minus 2 is 3. 3 times 8 plus 2 times 2 plus 1 times 4. So now we have 20 plus 24 plus 4 plus 4. And that'll leave us with 44, 48, 52. And if we look at our answer, it's 52. So it takes a little bit of work, but you can find it without being given the function. So it can be useful. Okay. Next, we're going to learn about what's called the fundamental theorem of calculus. So you think if you're in a calculus course, you're probably learning this at least at the beginning of second semester at the earliest. And how are we learning the fundamental theorem just now? Well, this is a theorem that connects the two big ideas of calculus that we're doing, which are derivatives and now integration, which is the area under the curve. So I'll open a whiteboard. What the fundamental theorem says is that if we have some function here, the area under the curve can be found a very special way. So imagine we were going to take a Riemann sum to approximate the area of this. We can draw rectangles like this. Let's pretend this goes down a little more. just to make it easier to notice. Okay, this is a very bad graph, but we can see that we're getting approximation. I'm very roughly sketching this. This is a pretty good approximation, but we still have all these weird little spaces over here, and it's not really that accurate, and it's also very tedious. So we noticed that as we get more rectangles, our other one only had 4 rectangles, but this one has, I don't know, around 10. So it's getting more accurate. The other one had more space in between the lines, in between the rectangles, but this one does not have as much. So we're noticing as the number of rectangles increases, our function or our approximation of the area under the curve is getting better and better. So we notice that if we keep chopping these up into, smaller pieces, then instead of here, we'll go like here. And instead of here, we can go like here and there. The point is, it's getting more accurate the more rectangles that we add. So how can we write this as the sum? Because if we take infinitely many of these rectangles, as we keep adding more, the length of the rectangle, this little distance right here, we'll call that delta x, it's going to keep getting smaller. So the area of each rectangle is going to get really small. But as that area is getting small, we're getting more rectangles. So it kind of balances out, but it gives us a more accurate approximation. Now you're probably thinking, how do we add infinitely many rectangles? That it was tedious with only 4. So a way that we can do this is, first we can write out what we know. We know that the Riemann sum is the sum, that's the summation sign, from I equals 0 to n. N is just how many rectangles there are. Actually, I don't think we need that. It's not really necessary. We can just say the summation. So when we add all the rectangles of f of x, so actually, how can we find the area of each rectangle? It's delta x times the value of the function at that point, because that is the height by definition. The height is just the y value, which is f of whatever that number is. So we can write this summation as the sum of f of x times delta x, because that's the width of our rectangle, or yeah, the width or length, depending on your preference, and the other one can be the height. So it's the summation of all of these. So as we take delta x to be really, really small, the number of rectangles to be really, really big, we take out this summation sign, and it becomes an integral. And this delta x, we'll still have f of x. That delta x, when it gets really small, so we have the limit as n approaches infinity. So as the number of rectangles approaches infinity, but their length gets really small. And as delta x, this length gets really small, we change it to dx, which is just the limit as delta x approaches 0. If we remember from our definition of derivatives, it's kind of the same thing as h in our difference quotient or our definition of a derivative. So this is a way that we can write this summation as it goes to infinity and gets as accurate as it can be. So now the fundamental theorem of calculus, as I talked about earlier, the accumulation of change and the area under the curve. So the area under the curve is related to the accumulation of change, which is related to the derivative. So what this theorem says is that the integral between 2 points, let's call this A and this B, or no, A and B. If big F of x is the antiderivative, so the derivative of this equals f of x. If big F is the antiderivative of f, then the integral between 2 points is f of b minus f of a. So it's final minus initial. And this is basically the fundamental theorem of calculus right here. But there's also something called indefinite integrals. So if we weren't finding it between 2 points, then we wouldn't be able to plug in an a and b. So the general form of an integral is we take the antiderivative of this f of x. So let's just say it's x squared plus 2x plus 5. I don't know, it's just some function. The antiderivative, we want to think what would have a derivative that is that. So this is called the reverse power rule. We learned the power rule in derivatives, and now we want to find out what will have this as a derivative. So we have x squared. We think, okay, so when we take the power rule, the exponent gets subtracted by 1. So to find the antiderivative of this, the first thing we have to do is start by adding 1 to the exponent. So we have x cubed. But if we just took the derivative of this, we'd have 3x squared and not x squared, which we want. So we have to divide by this new exponent, which is 1 over 3. And in fact, that is the antiderivative of this x squared part. Now to do the same thing for 2x, we do plus. Now we add 1 to the exponent. It's 1 right now because x to the first is x. So if it's 2, then it's x squared. But the derivative of x squared is already 2x, so we can just leave it as x squared. And then we have plus 5, the derivative, if we add, it's 5x to the 0. So if we add 1 to the exponent, we have 5x. And then when we bring the 1 down, it's still just 5. So plus 5x. But wait, there's no constant at the end of this. And that's because if we took the derivative of this, the constant could really be anything. So the graph could start here, could be the same graph that starts up here, because the derivative doesn't encode any extra constants at the end. So in an indefinite integral, we add plus c, just to indicate that there can be any initial condition for this function. And that's how you do an indefinite integral. So now, if I wanted to find the area under the curve between, say, x equals 5 and between x equals 2 and x equals 5. And you'd write this, by the way, as the lower value and the higher value. So the area under the curve between 2 and 5. So the way you find this is with our fundamental theorem of calculus. You take this antiderivative and evaluate it. That means evaluate it at between x equals 2 and x equals 5. So we do this function evaluated at 5 minus the function evaluated at 2. And if we notice, this c doesn't have anything it's being multiplied by. So when we're doing definite integrals, which means between 2 points, not just an indefinite integral without any 2 boundaries, we can neglect this plus c and just focus on the rest of the function. So I'll erase my beautiful, not that. I'll erase my beautiful graph over here, or at least part of it. So we can keep going here. So if we do f of 5 equals 5 cubed is 125. 125 over 3 is not 25. It's 125 over 3. Plus x squared. 5 squared is 25. Or we could write this, it'll help us later to write this as 75 over 3, just so we can have a common denominator. And plus, if we plug it into x equals 5, 5 times 5 is also 25. So another 75 over 3. Then we can ignore the c. So this adds up to 250 over 3. But that's not our answer yet. We have to subtract the value at 2. So f of 2 equals 2 cubed is 8, 8 over 3, plus 2 squared is 4, so 12 over 3, plus 5 times 2 is 10, so 30 over, I'm going to rewrite that. 30 over 3, and then the c can be neglected. So when we add all these together, we get 42 plus 8 equals 50 over 3. And now we do f of 5 minus f of 2. And 250 minus 50 is 200 with the 3 in the denominator. So this is our area of this function between the points 2 and 5. And that is because we're taking infinitely many really, really small rectangles and getting a very accurate approximation for the area under the curve. Okay, so that is a big concept of integration. It's just as big as derivatives. It's the second big idea of calculus. So now let's do a problem. Evaluate the definite integral of this. So notice that we can split this up into two smaller pieces. X squared minus 1 over x can be split into x squared over x minus 1 over x. So that's x minus 1 over x, or x to the negative 1. So now we'll take the integral of this. Remember to add that dx at the end of there because it's a bunch of really small rectangles. And now we find the antiderivative. So x, the exponent is 1. We add 1. We have x squared. The 2 jumping down gives us 2x. We just want x, so we have to divide by 2. So it's x squared over 2. Now, what's the integral of 1 over x? If you remember from derivatives, there's a special function that has a derivative of 1 over x. And I'll hope that you remember that it's ln x. So minus ln, and we just use absolute value because ln can't be negative. But it's just ln of x. And then evaluated between 1 and e, because those are the boundaries that it gives us here. So, actually, no, we don't need the plus c here because it's a definite integral, not an indefinite integral. So now if we plug in e over here, we have e squared over 2 minus ln of e is just 1 because e to the 1 is e. So minus 1, that's our f of e. So this minus f of 1, 1 squared is 1 over 2, 1 over 2, minus ln of 1, which is 0 because log base anything of something is 0. Log base anything of 1 is 0 because something to the 0th power is just 1. So that minus 1 minus 0. Sorry about that. Erase that. So then if we just have minus 1/2, then we have e squared minus 3 over 2 because negative 1 minus 1/2. Then e squared over 2 minus that over 2, we can group the 2's. And we have e squared minus 3 all over 2. And that is our first answer here. And it's right. So that's just an example of a definite integral, finding the area under the curve without approximating, finding the actual answer. And I think this is easier than doing a bunch of rectangles, but that's up to preference. So now this is a piecewise function. How can we do this? Now we can think of doing this piecewise function by splitting it up into two intervals. So we're finding the integral between 0 and 4, and this piecewise function separates at x equals 2. So we can do the integral from 0 to 2, or when x is less than or equal to 2, of 3x dx, because that's this function right here, And then if we use our rule, then we get 3/2x squared evaluated between 0 and 2, which equals 2 squared is 4. 4 times 2/3 is 6. 6 minus 0 equals 6. So between 0 and 2, it's 6. And now between 2 and 4, the rest of that interval, you have to find the integral interval, sounds similar. This is the integral between 0 and 4 of this function is just 3, this part of the piecewise function, just 3 dx. And if we remember the antiderivative of a constant, you just add an x at the end, equals 3x evaluated between 4 and 2. So 4 times 3 is 12, minus 6 equals 6. So both of these sections are 6, so we just add the two parts and we get the whole. Okay, this is what's called the second fundamental theorem of calculus. There are a lot of fundamental theorems apparently, but only two. So we know that derivatives and integrals are inverses because the integral just takes the antiderivative. So taking the derivative of that should just give us with the original function. But if we're taking a definite integral, then that's when the values are plugged in. So problems like this give us a value that has x in it. So between that and a constant. So, and we're taking the derivative of that. So we're not going to take the antiderivative of sine t squared, which you could, it's just not that efficient. So if we want to do this, the answer, it's you plug in this value of the higher value of the integral, the upper bound, we plug that into the function. So instead of t squared, we plug in 2x for t. So we have sine of 2x squared which equals sine 4x squared. But we're not done. If this were just x at the top, then we would be done. But this we have to treat as a function on its own. If we remember from derivatives, we have to use the chain rule. So we multiply then by the derivative of this 2x, which is 2. So actually, I should write that separately. So that's sine of 4x squared. Now we have 2 sine 4x squared. And that's the second fundamental theorem. That's not as bad as the first one, not as much conceptual rigor. So it's just that. This is another example of an indefinite integral. So remember, if we have 2x to the first, so the exponent becomes 2, you add 1, and then x squared, the derivative is already 2x, so we just have x squared. But remember, if it's an indefinite integral, we cannot forget the plus c. You will lose points on a free response question if you do not include the plus c. Make sure to include the plus c. It's very important because just x squared is not the only function that can be this integral. So x squared plus c. So the methods we've learned for integration so far are pretty simple. They only work for certain kinds of functions, polynomial functions that are really simple. It's just something times x to a certain power. But what if we have more complicated functions like we did when we were taking derivatives with the chain rule? So this technique is called U substitution, and it's going to be kind of like the anti-chain rule. So instead of for derivatives, it's for integrals. So if you remember, the chain rule says that the derivative of f with respect to x, so df dx, equals, if this has some function u in it, let's say u equals x squared plus 2, and that's in parentheses and raised to a power like it's that squared, then that inner function is going to be its own function. So we can set u equal to that, and we know that df dx is equal to df du, so the derivative with respect to u, this function, if we just treat this function as a variable, then times the derivative of that function, du, with respect to x, because when we're taking it, we're having x as the variable instead of this u that we've made up. And if we look, these du's cancel out and we're left with just df dx, which is what we were originally trying to get. So that's just the chain rule restated. And we're gonna have to do the opposite when we're doing integrals with this. So now let's go to an example, because I think that's the best way to see this in action. So we're asked to evaluate the definite integral of this function. And if we notice, this 1 minus x squared is inside of a square root. So this is like an inner function. So when we see something like that, or something raised to an exponent of a power like this, if it was, let's say, e to the 1 minus x squared, we would know that 1 minus x squared is going to be our u, because that's a function that's inside of another function, in this case, the square root function. So what we want to do is define u equals 1 minus x squared. So then we'll be left with the integral between 0 and 1 of x times the square root of u dx. But if we notice, our variables don't really match up. We have u and dx, which we can't have. So what we can do here is, well, what we have to do here is set everything in terms of u. So if we define the derivative of u, du dx, as the derivative of this, which makes sense, you're taking the derivative of u and your variable is x. So derivative of 1 is 0, derivative of negative x squared is negative 2x. So it's just going to be negative 2x. And what we want to do is substitute this du, or something with this du, into this dx expression. So we want to isolate dx, and we can do that. We get du equals negative 2x dx, and then dx equals negative 1 over 2x du. So now we want to plug in this expression for our dx, because that's equal to dx. So now we'll carry on our work somewhere over here. We substitute that in, we get negative 1 over 2x times du times this x that was already here originally, times the square root of u. And now if we simplify this, we notice we get, when we're multiplying x and negative 1 over 2x, the x's cancel and we're left with just negative 1 over 2, and then square root of u and du. And we want to take the integral between 0 and 1. But remember, this 0 and 1 was for our x, so that might not be the same later. Well, no, we have to check to make sure that that matches with u. So instead of having these boundaries in terms of x, we want them in terms of u. So when x equals 0, if we plug in 0 to this u expression, we get 1 minus 0 squared, which is 1. So instead of 0 at the bottom, it'll be 1, and that'll be our lower bound. So then we have the 1 at the bottom, and our upper bound is 1 originally in terms of x. So now we plug that into our u expression. We have 1 minus 1 squared, which is 0. The integral between 1 and 0. Notice this is the same thing but backwards. So it's going to be the negative of whatever it originally would have been if we had kept our old variables. And then of negative 1/2 square root of u du. So what we can do here is take this negative 1/2 x out to the front. So we'll have negative 1/2, because the coefficients don't matter in integration. We'll have negative 1/2 times the integral between these 2 points of the square root of u. But if we're taking it from the lower bound to the higher, or the higher bound to the lower bound, it's going to be negative. And our coefficient is negative, so these can cancel out if we change it to 1/2 instead of negative 1/2. Change the boundaries instead of from 1 to 0, from 0 to 1. So we can rewrite this as 1/2 times the integral from 0 to 1, which is what we had originally, but notice we had to do something with a negative sign, times the square root of u du. And now if we take the antiderivative of du, which is u to the 1/2, we get 2 over 3 u to the 3 halves. 1/2 times u to the 3, or 2/3 u to the 3 halves, and that's evaluated between 0 and 1. So what we can do is multiply this out. So instead, now we'll get 1 times 2 is 2 over 3 times 2 is 6. So we'll get 1 over 3 u times, or 1 over 3 u to the 3 halves between 1 and 0. But before we evaluate this at the points 1 and 0, we have to plug in our original expression for x. Actually, no, we don't. That's another way, which I'll show just after this. But now if we plug in 1, we get 1/3 times u to the, times 1 to the 3 halves, which is just 1 times 1/3. 1/3 minus our lower bound, 0 to the anything is 0, times 1/3 is 0. So that's 1/3, which is going to be our answer. But I want to show you another way you could have done this. Instead of changing our bounds right here to be in terms of u, I'll erase some of this up here. Instead of changing our bounds to be in terms of u, for this step right here, you can continue on doing this in terms of x, and then later we'll see what we can do. So now this becomes -1/2 times the integral between 0 and 1 square root of u du. Remember, the square root of u, the antiderivative, is 2/3 u to the 3 halves, so -1/2 times 2/3 u to the 3 halves between 0 and 1. So now this is the negative of what we had in our other way of doing it, but it won't always work out that way. Now what we need to evaluate it, or before we evaluate between 0 and 1, we substitute this u back into our expression for u here before we evaluate it at the 2 points. So we'll have -1/2 times 2/3 times 1 minus x squared, all to the 3 halves, and that between 0 and 1. So I'll erase our other method over here just to make some room. And now if we evaluate this between 0 and 1, at 1, we get 1 minus 1 squared is 0 times everything is just 0. And then minus, if we evaluate it at 1, or at 0, we get 1 minus 0 squared is 1 times 2/3 is 2/3. That to the power of 3 halves, or actually, no, never mind. We do to the power of 3 halves before we multiply. So 1 minus 0 squared is 1 to the power of 3 halves. It's still 1 times 2/3 is 2/3. 1 times 2/3 is 2/3. Times -1/2 is -1/3. So we have 0 minus -1/3, and it's a negative times a negative, so it's positive. And then we get 1/3, which was our original answer. I'll write that better so you can see it. And if we look at 1/3, that's going to be our answer. Okay. Now we're getting into some applications of integration. But first, before this unit, another part of this unit, the first section, it's very simple, so I didn't think we needed an entire problem for that. It's just finding the average value of a function on an interval. So we know that derivatives and integrals are inverses. So if we want to find the average value of a function, actually this doesn't really have anything to do with derivatives, but basically what you do, 1 over, so let's say we were trying to find the average value of some function between 2 and 5. We'll use 2 and 5 again. So what we do there, we'd find the integral of f of x dx divided by, so times 1 over the difference between those points. So 5 minus 2 is 3. No, 5 minus 2 is 3. So it'd be 1 over 3 times the integral of that. That is the entire 8.1. I didn't think we needed an example. It's just the two endpoints. You plug them in and divide them by the difference. 1 over the difference. No, you divide by the difference, multiply by 1 over the difference. So now what we can do is kind of the same thing as something we did in unit 4, which is connecting velocity, position, and acceleration. So instead of having derivative of position is velocity, and derivative of velocity is acceleration, we just do the opposite. So we know integrals and derivatives are inverses. So we have the integral of v of t dt equals position, and the integral of a of t dt equals velocity. And now we just do the same stuff that we did back in unit 4. So particle moves with the velocity according to this function. If at time t equals 0, x equals 2. So that's what we call an initial condition, which we'll go into more in differential equations. But that just means that the position, so we know the position at time equals 0 is 2. So that's our c. Because if we had an indefinite integral, we'd still be left with a constant that can vary, or that can be different. So if we know the initial position, then that we plug that in for the c. So in this case, it's 2. What we want to do is multiply this out because it's going to be hard to work with that. So 2t squared minus 10t plus 12. Okay, we can take out a common factor there, but just to save some time, I won't. So we know that's the velocity. Now we can integrate that. So we have 2 over 3t cubed minus 5t squared plus 12t. And then I'll erase these. Hopefully you can remember that the relationship between velocity, acceleration, and position from unit 4. And then we know that our c, which we would normally have in an indefinite integral, is 2. So this is the position function. So we're trying to find the position of the particle at time t equals 3. So we just plug in 3. So 3 cubed, 27 times 2, 54. 54 over 3, that's divisible by 3. I'll divide it in a second. Minus, that equals 3, so 945 plus 12 times 3, 36, plus 2. So negative 9, negative 7, plus 54 over 3. Now I'm going to find out what 54 over 3 is. 54 over 3, 18. I probably should know that. So 18 minus 7 equals 11. And in fact, that's our answer. So it's the same thing that we did in unit 4, it's just the opposite, and with an initial condition. Now we're looking for the area contained between curves. So imagine we had some function that, and some function that, and we want to find this area right here, and that's enclosed by the two curves. So the way we can do this, it's kind of like finding the area under this curve, the higher curve, and then you subtract the area under this whole curve. Wait, hold on. Not that. Actually, let's just graph these into Desmos. erase my little drawing there. We had x squared and negative x squared plus 8. X squared, negative x squared plus 8. So it's this region right here. So we're finding this area. Now we need to do is we have to subtract these to find the area in between the curves. So we can do this. First thing we have to do actually is find the points that they're equal. These are going to be our bounds. So it's these 2 points. We can see that they're 2.82. Actually, no, not 2.82. They're 2 right here. But we'll have to solve these without seeing the graphs. So we set these equal. We find the values where they're equal. So we have x squared equals negative x squared plus 8. Add x squared to both sides. 2x squared equals 8. X squared equals 4. X equals 2 and negative 2. So those are our boundaries. It's just when we set them equal, that's how we know when they cross and go on to different paths. So now we're going to look for the integral between negative 2 and 2 of these functions subtracted. So what we sort of need to do is take the higher function minus the lower function. So the blue one minus the red one. But there's kind of a way we can get around finding which one is higher. And we can just do the lower one minus the higher one, or whichever one we want, because we won't know. And then if it's negative, then we kind of just flip it around afterwards. So it's kind of a little shortcut, or you can just put absolute value signs around it. But it's always going to be positive. So x squared minus negative x squared plus 8. So then we have the integral between negative 2 and 2 of 2x squared minus 8. So we have to the third. So 2 over 3 x to the third minus 8x, evaluated between 2 and negative 2. So then 2 cubed is 8. 8 times 16 over 3. Erase this. 18. No, not 18 over 3. 16 over 3. 8 times 2, 16 over 3 minus 16. So that's going to be 48 over 3. So negative 32 over 3. You'd get that by doing a common denominator. So you do that, and then minus the value at negative 2, which is going to be, again, 16 over 3. And this time it's plus 16. So this is going to equal 16 plus 48 is 64 over 3. And now we have to do final minus initial. So actually this was our final, that was our initial. So negative 32 over 3 minus 64 over 3. We notice it's going to be negative, but then we can just flip it later. 64 minus 32 is 96. Negative 96 over 3. And that should actually be divisible by 3. We'll see. 96 over 3. So that's negative 32. So now that's negative. So we're just gonna kind of make it positive. Oh, sorry. 32, that seems a little high. Hold on. If we go back, we have our antiderivatives evaluated between see if that's an answer. Not that one. Okay, we have to find out what we did wrong or what I did wrong. So 16 over 3 minus 16, negative 32 over 3. And then, so that's for 2. So now for negative 2, 16, plus 16, not minus 16. Let's try this again. So this is our antiderivative. I think 2x squared minus 8. So we have 2 over 3 times 2 cubed minus 8 times 2. So then we have 8 times 2, 16 over 3. 16 over 3 minus 16, which is 48 over 3. And then we get negative 32 over 3. Maybe we do need to do the functions in the other order. Try it again using our other function first. So then we'll have the integral of negative x squared plus 8 minus x squared. So we have the integral of negative 2x squared plus 8 dx between, what was it, 2 and negative 2. And now we take the antiderivative, we have negative 2 over 3 x cubed plus 8x between 2 and negative 2. So now we do 8, negative 16 over 3 plus 16. So 32 over 3 minus, we plug in negative 2. That's why, because that's not positive, that's still negative. Then we do negative 2x cubed, which is negative 8 times negative 2, 16 over 3 plus 16 over 3 minus 16. So that's going to be negative 32 over 3. So then we're just adding that. It's 2 times 32 over 3, 64 over 3. And it's positive. Okay. So that's how you find the area between curves. You just subtract them. And yeah, if you take the one on the top, it doesn't matter. I just made a sign error. It wasn't that we took the wrong one on the top. Okay, now this is a rather annoying one. This is where the function crosses the x-axis between more than 2 points. So we're finding the area between this and y equals 0. So you have to find the times where that equals 0, all of them. So we have to set them equal. Minus 20x squared plus 60. Actually, that might not that's going to factor and not be as bad. So over 10. But the 10 we can just multiply and it doesn't affect our thing. So x to the 4th, that factors as x squared minus 16, x squared minus 4. And that reduces again to x plus 4, x minus 4, x plus 2, x minus 2. So this is a lot of zeros. It's a little tedious, but you just got to find the integral between each of these points. So yeah, I wish I had better news for you. So we'll take the integral between negative 4 and negative 2. of this whole thing. So we'll have x to the 4th over 10, so x to the 5th over 50. I'm gonna have to clear that. X to the 5th over 50 times 5 is x to the 4th over 2. Yeah, so x to the 5th over 50 minus, so that's just going to be 2x squared minus 2 over 3x cubed plus 64 over 10x, which simplifies, but actually we'll just simplify it, 32 over 5. And we're going to evaluate this between -4 and -2, and also along all these other intervals. It's going to be tedious, so if you don't really care, just skip a little bit. But the basic idea is you just do this for all the points. So -2 to the 5th, that's -32 over 50, -32 over 50 minus -2 to the 3rd is -8 times -2 over 3, 16 over 3. Actually, it's probably plus, yeah, plus that, 32 over 5x, x is -2, minus 64 over 5. And we're gonna have to add that all up, aren't we? So I think our least common denominator is going to be 150, which is also kind of annoying. Multiplied by 3, 32 times 3. What is that? On a test, you would not be able to use a calculator for this, but to save time, I'm going to. So 96 over 150, -96 over 150, plus 3 times 50 to get 150, 16 times 50, that should be 800. Wait, 16 times, yeah, 800 over 150 minus that times 50, 150 over 5, not 50, 30. 30 over, oh, sorry. $64 times 30 minus 1920 over 150. Now you add, subtract, and whatnot, and you get plus 96, 1216, and that is between -2 and -4. I actually don't think it's going to be a good use of our time to do the rest of these. The idea is you do it between -2 and -4, and you do it between -2 and 2, and it's the same process. Then you do it between 2 and 4, and there you have it. So I don't think it's going to be a good use of our time to keep multiplying these out, because it's just not worth it to show the same thing multiple times like that. So the next thing is approximating volume using cross sections. So I'm actually going to go over to this AP Calculus cheat sheet that I found online. I think it's from Weebly. So this just has formulas to everything in the course. I could post the link in the description. But it also has good visualizations, and it has the formulas that you need. So area by cross sections, we're taking the area of a curve, and we're making it 3D by approximating it with little 2D shape, a bunch of almost 2D shapes, just with really, really small width. And then they make it they go into these shapes. So it's just adding a bunch of little either rectangular prisms with a square base, or there are a lot of them. So cross section by squares, it's just the area for a square inside of an integral, but then you use the function instead of the length. So if your function was, let's say x, f of x equals x, then in this function you'd find the integral of x squared between whatever your endpoints were, and then you just evaluate the integral. Equilateral triangles, there's a way to prove this square root of 3. I can be good to prove this. Just memorize the formula. You don't want to end up like me trying to figure it out and having to do some geometry. It's square root of 3 over 4 times the same thing for the square. But just remember that it comes from the area of an equilateral triangle. When you find the height in terms of the side length, just remember this formula. It'll save you some time. Isosceles and right triangles, that's just if you had it like this, no, that's not a right triangle. That's a right triangle. So if a leg is the base, then the length of the leg is just going to be our dx. So, but then the height is going to be the function. So it's going to be just the area of a triangle. The function is the height. Space times height over 2 squared, right? Oh, it's isosceles. So these are equal. The area is this times this, or this side times this side over 2. It's just the function squared divided by 2. Now if the hypotenuse was the base, so if we made, no, not that. If we did this, and that was 90, was a right angle, then it's going to be 1/4. And again, I'm not going to prove it to you just to save time. Just remember it's 1/4. Now semicircles, I can prove in minimal time. You should probably still remember it, but it's pi over 8 because a semicircle, remember, is just a half circle. So the area can be given by pi r squared over 2. So if r is, but remember the function is giving the diameter. This part right here is the function, and that's the diameter. So we need the function over 2. So it's r pi, this is r, this whole thing is squared. And then remember, we have to divide this whole thing by 2 because it's half a circle, not a full circle. So this squared applies to the f of x and the 2. So we have f of x squared over 4. F of x squared over 4 times pi over 2. And then we can take the pi, when we multiply, we get pi over 8 times f of x squared. But remember, we're going to do an integral of that. But then the constants can stay on the outside. Oh, wait, sorry, it's not. That's not, this right here is not pi squared. That's just the 2 from earlier. I'll erase it so it's not confusing. Pi. So pi over 8 is our coefficient. So now it's going to be this formula here, pi over 8 times the integral of that squared. And pi over 2, this one, the radius. Oh, actually, that was, the radius is the function instead of the diameter being the function. So you can save yourself that squaring of the f of x over 2. And it's just pi over 2 times that. I recommend memorizing these formulas. Some of them should be obvious, like the square one. You're just squaring the inside. But some of these are kind of complicated to figure out. So I'd recommend just remembering them. So the next thing that we do with this volume idea is called the disk method. So we think about having this function, then we revolve it around, in this case, the x-axis. So you see here, it goes like this, and then it loops around in 3D. So it's kind of like, yeah, it wraps around the x-axis. So this, it's pi r squared. So if we divide this up into a bunch of little disks, so a bunch of little disks, imagine each of these is a disk with a very small width, dx, so it's almost a circle, but not quite. Then an integral is where we sum up infinitely many of those, or the limit as the number approaches infinity. And so we know that the function, the height of this function is going to be the radius because it's from here to here. That's the height of the function. So that's the radius of the circle. And what's the formula for area of a circle? It's pi r squared. And if the function is the radius, and we're taking an integral, it's the integral of pi r squared. And this pi can go up front. So we have pi times the integral from a to b. So 2 points that you choose. Dx, remember that. And then r is our function, f of x squared dx. And that is where that comes from. You're just taking a bunch of little disks and adding them up to find the area of this. Now, the same thing applies to the y-axis. So if you're revolving something around the y-axis instead of the x-axis like it is here, so vertically, or you're rotating horizontally, but around a vertical axis, like this pen here, you're rotating around here, and before we were rotating like this. So now, instead of functions of x, we're just going to do functions of y. So let's say our function was x equals 4y squared. That's a function of y, not of x, because normally we have y equals something with x in it, but now we have x equals something with y in it. So this is a function of y, and we plug this into that same integral, but as a function of y, and integrate it with respect to dy, and it's the same formula, pi r squared. So now, if we revolve it around just some random horizontal line, so let's say y equals 3, then it's not going to be exactly the same because this is our function and we're revolving it around this line instead of this line down here. So the way that we do this, you can see the formula here. It's just the same thing, but so it's the integral pi, instead of just f of x squared, it's f of x minus whatever that y equals. If it's y equals 3 minus 3, so in this case it's 3, then that whole thing squared from a to b. And that is how you do it around any line. And the same thing applies to the vertical line. That's just for horizontal lines. But with the vertical line, remember that's going to be around the y-axis, so we need it as a function of y. And usually they'll give you numbers that aren't too bad to work with as functions of y versus x, but I could be wrong about that. Always be prepared to isolate an x or a y. So that's the disk method. Now, something very similar is the washer method. So if you think of a washer like the tool, the washer, you have, it's like a donut. You have a circle, and then there's a little bit of area, and then there's a hole. So if we had a circle like this, and we knew the radius of the bigger circle, our big equals 5, and our small equals 2. And this is a hole, so we don't care about what's in there. We don't want to include that in our area. So to find the area of that, normally in geometry, we do the area of the big one minus the area of the small one that we're not including. So pi r squared, 25 pi, minus pi r squared again, minus 4 pi, because 2 pi times 2 squared. So that's 21 pi. Now we can apply the same thing for our disk method that we just did in what's called the Walshart method. So now we're revolving around the x-axis in this case. So if it's not exactly around the x-axis, if it's bounded by two functions, then we have to do just the areas. So we have to subtract the areas. So we think about it as the integral of f of x squared, so pi, that's the total area, then minus the area of the smaller circle, which is pi times the integral of g of x, quantity squared dx. Don't forget the dx, I've probably forgotten the dx. They will not give you credit if you forget this dx, so very important. And then that's where this comes from, because you can combine the integrals, they're like terms, so then you end up with this right here. And then again, the same thing applies to the functions of y, and pretty much everything is just the same as with the disk method, you're just subtracting that other function. So here it's just functions of y, same thing with respect to y. And now you're doing it around a horizontal line. You subtract whatever that y equals. They're showing it as k here. So we take the area of the big circle, which we know how to find it wrapping around k, then minus the area of the smaller circle, which it's the same formula. And then same thing for a vertical line instead of a horizontal. And we get all these cool shapes from doing this, but you're not gonna have to draw those, don't worry, it won't be tested on your drawing ability. And this is pretty much integrals and applications of integration. Oh, one more thing. When you're asked for an integral in context, I'll just open a whiteboard. So if you're asked for what does like the integral represent in some case, you'll usually be given something like a population is changing at a rate equal to some function f of x, they'll give it to you in people per year or any time unit, something per time. So for taking the antiderivative, remember the derivative gave us a little per second or per year time thing at the end. So for taking an integral, take away the per year, and so the integral of f of x dx just gives us the number of people, like the population at that time, not the rate of change, which we're given. This is the number of people. And we have to specify if it's in a free response question. This is the number of people. We have this amount of people in the population at some time. X it'll probably be t, not x, because time. There are this many people in the population at that time. You can't forget to mention what time it's at, because it's not always that many people, it just happens to be at the point that they're asking for. And so that's integration. We did it. That's the end of the Calc AB course. Calc BC still has 2 more units, but if you haven't seen my other videos, go check them out. I'm also going to make a review for the whole course, just in a nutshell, to summarize everything that we've learned. But thanks for watching this video. See you in the next one, whenever that may be.